Well, thanks for the opportunity to be here today. I want to talk to you today about a topic I think everyone in the oil and gas industry should be aware of. And as you can see from the slide behind me, that is the use of oil and gas technologies to dramatically improve the economics of geothermal power production. I'll talk about those technologies, and I know some of you in the room here have actually been involved in some projects out in Utah. Where's Bill? Bill Thomas? Bill's company actually had one of the rigs that were deployed to drill a record-setting well out there, so we'll talk a little bit about that. In this presentation, it's going to be a pretty high-level overview, so I hope as we get towards the end of the presentation, we'll have time for some questions and maybe dive deeper into a few of the different technologies. And so with that, let me get started. I'm going to start out with some general discussion about heat to power. And I think as most of you know, there's an enormous amount of heat beneath the surface of the Earth. If you were able to travel to the core of the planet, it'd be about 10,000 degrees Fahrenheit. Obviously, we can't do that today. You know, we can drill a few miles into the Earth's crust, but even in those areas, as you can see in the bottom right, you know, there's areas where there's an enormous amount of heat flow. That heat coming up from the center of the planet, that heat is sufficiently powerful to move plates around the planet, open ocean basins, close ocean basins, create enormous volcanoes, and that manifestation of that heat should help us understand that there's enough energy in the Earth to basically satisfy all of mankind's needs for centuries and centuries to come. The good news is that there are a lot of different ways to use that heat. So if you look at this slide here, starting on the left, very, very shallow applications with the heat pumps. I don't know, anyone here in the room have a heat pump in their home? Okay, one person in the back. So heat pumps are a way to heat and cool your home very efficiently. In some parts of the world, they're deployed at scale. As we go further and further to the right, we're getting into different types of applications, which are both more complex, but also more significant as far as the amount of energy we're harvesting and utilizing. And what I'm going to talk about today is power generation. This is where we take heat of sufficiently high temperature and use it to generate electricity. And on the slide, I think you can see I've got three different types of power generation outlined. Hydrothermal, which is where we are basically using natural systems within the Earth's crust to access that heat. So in the US, that's mostly fractured rocks with very high temperature water in them. We put wells into the ground, we extract that water, we can run it through a turbine. Good news about hydrothermal is the US is the world's largest producer of geothermal power. And almost all of it is hydrothermal. So, you know, you think about energy dominance, we are the biggest player in geothermal, not just oil and gas. But there's some exciting things happening in new approaches to how you can utilize that heat to generate power. And I'm going to talk about something called enhanced geothermal systems, EGS. This is going to be something that looks very familiar, I think, to everyone in the room, because what we're going to be doing is using hydraulic fracturing to create a artificial fracture system. We're going to pump water through like you would do in a water flood, and that water moving through the rocks is going to harvest the heat, and we'll generate power when it gets back to the surface. And there's also an approach called AGS, Advanced Geothermal Systems, where we never let that water get out of well bores. Basically, the water would be going around a U-tube in the subsurface and brought back to the surface to generate power. So I'll talk a bit about that as well. As I said, this is good news for America in that we are the world's largest producer. Most of that production's out west. So if you look at the map on the left first, the areas that are in green are areas where you have exceptionally high heat flow coming out of the Earth. If you look at northwest Wyoming, on the border with Idaho and Montana, Rick and I were talking. He spent some time right up in that area when he was with Amoco. You know, that's the Yellowstone hotspot. You know, the manifestation of that heat is the geysers and the recent volcanic activity. You can see a number of other areas out west. I've denoted three of the big geothermal power producing locations. So the geysers is the world's biggest geothermal field. It's located in Northern California. and then 2 other very large fields, Salton Sea and McGinnis Hills, both in the top 4. So lots of good news about where America stands as far as geothermal power production is concerned. However, you've probably already looked a bit at the diagram on the right. That's kind of the downside. I mean, so we're the world's biggest producer of geothermal power, but today it's really a trivial amount of the entire US's electricity grid. So less than 0.5% of America's electricity is generated with geothermal. So this story is going to tell you a little bit about why that is so and why this is about to change in a big way using oil and gas technologies. On the why, there hasn't been more geothermal successes over the last half century. This slide here describes it. I've got hydrothermal on the left, EGS on the right. The punchline is for hydrothermal, if you can find one of these big accumulations like the geysers, they can be incredibly profitable. But the exploration success rate has been horrific. These things are incredibly hard to find. If you look at that diagram up there, what I'm trying to show is a cross-section through the Earth's crust. We've stripped away all the rocks. Those planes are meant to represent faults. And in a perfect hydrothermal system, what you're looking at is water flowing along the fault systems to the wells. And then the well, you lift that water out of the subsurface, and as I said, bring it through turbines at the surface. So if you can find a system like that, really your only significant subsurface cost is the drilling. We're not fracturing the rock. We're not spending that much money on it. So if you can find a big hydrothermal system, you're in good shape, but they're very, very rare. Or at least with the technologies used to date, have been hard to find. I'll talk about that a little more later. On enhanced geothermal systems, the problem has been that although for 50 years people have tried to use hydraulic fracturing to create effective fracture networks to connect injectors and producers, the track record has been dismal. And part of the reason for that is what we've learned over the last 20 years in unconventional oil and gas. As you know, in unconventional oil and gas, we use horizontal wells. Up until just a few years ago in geothermal, there'd never been a horizontal well drilled. So trying to connect vertical well or fractures coming off of vertical wells turns out to be incredibly hard. You don't create that much fracture area. The reason we don't use vertical wells in places like the Permian Basin or here in Oklahoma to access those unconventional reservoirs is we just don't create enough fracture surface area. So one problem is you have a fracture surface area limitation. Another problem, which is shown on the map or on the diagram, is that when you create a fracture from one point in space, it generally creates a planar feature. And you can imagine trying to hit a planar vertical feature with other vertical wells. The track record hasn't been great, lots of dry holes. And then if you do connect an injector and a producer, what's tended to happen is you pump the water down, you're pumping a lot of water on just one surface, and it cools the rock very quickly. So these vertical EGS systems haven't lasted very long. So jump ahead to today. And here's what's being done to change the game. Let's start on the right this time. Horizontal hydraulically fractured wells. They have transformed the American oil and gas industry. Go back to 2005, our industry was slowly dying. Other countries had passed us as far as being the world's largest producers of both gas and oil. And then, of course, we learned how to extract oil and gas from unconventional reservoirs using horizontal wells, and today America is the world's largest producer by far of every type of hydrocarbon. Well, in geothermal, that well geometry is incredibly leveraging as well, because what it allows us to do is create an enormous amount of fracture surface area and basically eliminates the dry hole risk, because you're drilling through a series of fracture planes with a well going perpendicular to those fractures, and it's pretty easy to hit them. The other thing that's happened is shown by the pictures on the left. And that is, there's been some enormous advancements in drilling times in the geothermal space by using modern drilling technologies. And Bill, you know a lot about this. Bill was bragging to me, hey, we were out at Utah Forge and we drilled a record-setting well out there. And I'll show you some numbers in a minute. It really was record-setting. But it was taking the modern drill rigs that we have in the oil and gas industry and putting them into the geothermal space, whereas the rigs being used previously, frankly, weren't that sophisticated and not that capable. It's using PDC bits instead of roller comb bits. I mean, we haven't used roller comb bits in most oil and gas applications in America for a long time. PDC is a lot better. There were all kinds of paradigms about how in hard abrasive rock, like what you drill through in geothermal, you're never going to be able to use a PDC bit. Well, guess what? Those PDC bits work way, way better than the approaches used in the past. And then something called physics-based drilling, which is really simply understanding how you take all of the elements of the drill rig, the drilling machine, if you will, couple it with the type of rock you're drilling through, and coming up with the best approach for drilling a particular well. With all those things together, we've made some incredible advancements. I'll show you some numbers in a minute, but before I do that, just get you oriented as to where these breakthroughs occurred. They were actually out west in Utah and Nevada. So the project that Bill's company was working with was at Utah Forge, which is located in southwestern Utah. And at Forge, the US government funded a project to demonstrate that oil and gas technologies could be transformational in the geothermal space, and that demonstration project went great. This cross-section here in the center shows the geometry. I'm going to talk about Fervo Energy's project, which is more recent than Forge, but if you went back to 2002, 2003, at Forge they were drilling highly deviated wells. They didn't quite get to horizontal, but they got to 65 degrees. And in these wells, they set records as far as drilling performance. They broke those paradigms about how long does it take to drill a well in granite or metamorphic rock, the stuff that we call basement in the oil and gas industry. So from Forge, Fervo Energy, which is a private company, went out to Nevada and they drilled the first long horizontal wells in geothermal. 3,000-foot long wells, an injector producer pair, hydraulically fractured them, and demonstrated you could get significant flow rates through the fracture system. Flow rates high enough to make geothermal commercially attractive. And then they immediately moved back to Utah and offset the Utah Forge wells, and then they're in the process of drilling a 100-well development right now at what they call their Cape project. And this project's going to generate a 0.5 gigawatt of electricity. I'll show you the numbers on that and compare it to what's being generated in geothermal today, but that's a big, big project. So a lot of advancements have been made. Here's why Bill was so excited to say I was involved with Forge, because look at the graph on the left. Drilling performance and the type of rocks that were drilled at Forge used to take about 150 days for a single well. You can imagine with that length of time, the costs were high. Really, there was nothing which said EGS was going to be an attractive economic proposition. Well, at Forge, they went out and they cut that time by more than half. So the wells there got down to about 60 days. Fervo at their Project Red in Nevada duplicated that performance. They went fully horizontal, 3,000-foot long laterals. Today at Cape, wells are being drilled for less than 20 days. So about one-tenth the time and one-third the cost. So you can imagine if you can make that type of a change in your economic parameters on the cost side, you can really change the game. And what's happening right now is much like what happened in oil and gas with horizontal laterals. We're extending the length. So we've gone from 3,000 feet to 5,000 feet. The next wells at Fervo's Cape project are going to be 7,500 feet. No reason to believe we can't start drilling wells that are 2-3 miles long. So the extension of those well bores, as you know, in oil and gas have led to incredible economic improvements. And you're seeing some of the same thing in geothermal. And then look at the graph on the right. This shows the output per production well. And one of the things you're going to have to get your head around is in geothermal, the numbers, the volumes of fluid being moved are very, very large. So, in Permian Basin, a 3,000 barrel a day oil well is pretty darn good. We're talking thousands to tens of thousands of barrels of fluid. You got to move a lot of water to pick up enough heat to make geothermal economic. Prior to this campaign that I'm just talking about, the highest flow rates that have been achieved worldwide were kind of in the 7, 8, 9, 10,000 barrels of fluid per well range. So that's an average of everything from 1978 to 2022. And then you can see the scaling from there. Today at Cape, one of the wells has produced 70,000 barrels of fluid. So with those types of rates, you can dramatically change the economic results. And I'll show you the economic impact here on the next slide. Okay, so there's two sets of numbers on every bar. The number at the top of the green bar is the capital cost per kilowatt hour. So, or kilowatt of capacity, I'm sorry. Capital cost per kilowatt of capacity. So this is a way that people in the geothermal industry or in the electricity generation industry in general talk about projects. And then above the bar is dollars per megawatt hour. So that's taking all the cost over the life of a project and say, what did it cost to generate a megawatt of electricity? The numbers on the far left are terribly uneconomic. This is why almost nobody was pursuing EGS for all those decades in the past when it was possible to put a EGS project in the ground, but economically wasn't attractive. $335 per megawatt hour. I'll show you some comparisons 2 slides from now as to how that compares to a natural gas-fired power plant, a coal plant, wind, solar, but that just ain't good. And then you can see we scaled down. 2025 today, we're at about $85 per megawatt hour. That's drilling efficiencies, that's laterals instead of vertical wells, that's getting into somewhat hotter rocks. I'll talk about that part of the story in a minute. And where this could go is really what makes this exciting, because you can see a pathway to getting to some very low numbers. $45 per megawatt hour. I'm going to show you a slide here in a minute that says if you can get to that point, you don't have to think about this as a green energy source. I mean, you can say, I don't give a darn hoot about how much carbon I put in the atmosphere. You'd still want to do geothermal. So this would be, at $45, a highly commercial way to generate electricity that also is carbon-free, or near carbon-free. Before I get there, I want to talk a little bit about the other side of the equation. You think about, well, what does it cost for me to generate electricity? You also want to know how much is someone willing to pay me for that stuff. Okay, and this is exciting too, because in this space there's a lot going on. Power purchase agreements right now are being signed for over $100 per megawatt hour. And the drivers on that, and this is kind of particular for geothermal or any type of clean energy, but it is actually being driven by 2 things. One, there's certainly many parts of the world where they look at energy production and say, we've got to decarbonize. So you've seen these types of plots before, CO2 in the atmosphere going up, methane in the atmosphere going up. There's some debate about how big of a problem that is today, but if you keep putting CO2 and methane into the atmosphere at these rates for 100+ years, you're going to have a problem. So people are looking at going, okay, we've got to do something in this space and we're willing to pay more for green energy. But the other driver is much more right now in our face, which is all these hyperscalers with data centers and the electrification of vehicle fleets. The demand for electricity in America is growing at a phenomenal rate. Basically over the last, actually several decades, there's been almost no growth. You can see 10 years of actuals up there. What is that, 430 gigawatts on average, instantaneous usage per annum. Then look at the projection for 2030. You're now almost up over to 600. These are these giant data centers that are being built all across America that suck up gigawatts of electricity per data center cluster. So there's a need for the electricity. A lot of these hyperscalers want clean electricity. They're looking at nuclear, they're looking at geothermal. And because of that, you're suddenly getting people paying high prices, while at the same time, the cost of generating this type of electricity is falling rapidly. So that's a really exciting combination, one that you don't see in too many places, right? This is a bar graph which shows kind of the range of cost for different types of electricity generation projects. So building a new project today. At the top are all the quote unquote renewable energies. And this is with no firming cost. So this is saying, what does wind and solar cost to deliver a, what do they add in here, megawatt hour of electricity to the grid, but it doesn't take into account that you need some way to back up that wind or solar because the wind doesn't always blow, the sun doesn't always shine. Then down the bottom, conventional energy, gas, coal, nuclear. For gas and coal, no carbon price, right? Saying, okay, we're indifferent to how much CO2 goes into the atmosphere. And if you think about geothermal, with that graph I just showed you, back in 2020, no one in their right mind would have gone after this unless the government was paying for it, right? $300 plus per megawatt hour, nobody's going to make money on that commercially. Fast forward to today, now you're at $85 per megawatt hour. Suddenly it's starting to get pretty interesting. You're kind of right in the range, depending on where you're located geographically. You can't do this type of geothermal everywhere right now. But depending on where you are geographically, you might be amongst the most competitive sources of power out there. And then if you go to $45 per megawatt hour, it's kind of like, wow. As I said, this suddenly becomes potentially the electricity generation method of choice, regardless of what you believe about climate change. And that would be a great place to get to, because once you get to a place like that, suddenly money starts flowing in and people start getting very excited. Some of that excitement's already building. I've got a map here. We've been talking about the US, but this is going global. There's a project underway in Switzerland, so most of you know about Europe's kind of energy conundrum, in that they've been dependent on Russia for enormous amounts of their energy. That supply has been shut off. They're looking for, what can I do? Obviously lots of LNG coming from America, which is helping, but they're also looking at geothermal in a big way. They've got a project underway in Switzerland to drill horizontal wells and hydraulically fracture them. I went to Europe, 12, 13 years ago, trying to excite them about hydraulically fracturing oil and gas wells. The reception I got was very cold. I went and talked to Tidal and Schlumberger and asked them, what are you doing to get the French people behind hydraulic fracturing? And they kind of laughed at me and said, Greg, don't even bring up that topic. But suddenly, because it's going after clean energy and they need the electricity, this is suddenly becoming very important. Other places in the US, you can see up there, there's some work being done up in Oregon. And frankly, there's just a plethora of companies now starting up. People are purchasing acreage, so a lot of small startups, just like we saw in unconventional oil and gas, right? It wasn't the ExxonMobils, the Chevrons that were in there first. It was the small people, so you're seeing that in geothermal. But I can tell you, all the big oil and gas companies now have geothermal teams. ExxonMobil, Chevron, ConocoPhillips, Oxy, Devon. Devon's invested $100 million in Fervo Energy. So, a lot of my friends that are over there at Devon, we talk a lot about this. So, one of the reasons I always like coming back to Oak City. All right, so EGS is moving pretty quickly. I'm going to talk to you a little bit about hydrothermal, super hot rocks, and then AGS before I wrap up. So, I don't want you to get the impression that enhanced geothermal systems is the only thing out there where progress is being made. I'm going to start with an oil and gas analogy on the hydrothermal side. I've got a seismic section here and some production rate data on the right. This is from a ConocoPhillips operated field in Indonesia, or it was ConocoPhillips operated before ConocoPhillips sold the Indonesia business. And this is a 6 TCF gas field in fractured basement rocks. The storage and the permeability is fracture related in a popped up basement structure, wells drilled into it. We never got the fully horizontal wells, but we drilled a lot of highly deviated wells in there. And guess what? The flow rate per well is incredibly strongly dependent on the number of fractures you intersect. And how do you intersect fractures most efficiently in the subsurface? Well, most fractures are fairly steeply dipping. You want to go horizontal if you can. That's demonstrated by this information here. You've got flow rate. This is for wells drilled in the field versus the number of critically stressed fractures intersected by the well. By critically stressed, what that means is the fracture is oriented relative to the stress field in a way that allows the fracture to be dilated so that gas, in this case, can move along the fracture. I'm not going to go into depth, but look at well 11 in the top right corner. That well had an absolute open flow rate of a BCF a day. BCF a day, that's 1% of America's total gas production, or about 1% of America's total current gas production capable of being delivered from one well. So if you can intersect fractures efficiently, you can get tremendous flow rates. This is oil and gas side. Obviously on the geothermal side, it's more or less the same thing you're trying to accomplish. I want a lot of fractures intersections so I can draw a lot of hot water out of the ground. So a lot of interesting things happening in the hydrothermal space. Don't have time to go into great depth here, but the top is a series of like map view descriptions of fault geometries out in the western US that have proven to be places where hydrothermal deposits tend to be located. And I don't know how many of you have been out in the Great Basin, Nevada and Utah, but out there it's a terrain described as basin and range. So you have a mountain block, which is long and linear, and a valley, another long linear mountain block, et cetera, et cetera. Each one of those mountain blocks is bounded by a big fault. Big fault. So it's like a series of dominoes, just kind of tipped over. So I thought, when I got into this, well, it's got to be the big faults that have the biggest geothermal systems associated with them. Actually, it turns out that's not the case. Like 1% of the big geothermal systems out west are associated with big faults. It's almost all associated with kind of complex fault tips and areas where multiple faults intersect, small faults intersect, which makes it really interesting because figuring out where those faults go in the subsurface is a lot harder than it might seem. Seismic doesn't work very good in granites and metamorphic rocks. People are doing some really interesting stuff with using satellite data and machine learning to say where have faults recently moved, and then can I project them into the subsurface? And then of course my favorite is, well, I'm never going to be able to figure out exactly where all those small faults are, but if I drill horizontally through a bunch of rock, I'll just use the well to find the faults that I really want to intersect because they are active hydrothermal systems. So a lot of things happening in that space. Another area which is really, really interesting is getting into hotter and hotter rocks. So one of the things which was also a paradigm which, coming from oil and gas, I had to kind of rethink was, what temperature can we operate at? In oil and gas, getting, 300, 350, that's pretty hot, really hot. Most of the projects that I just talked about, Forge and Cape and Project Red, are in the 375, 400 degrees plus range. The reason you can operate in that environment is if you circulate enough water through the wellbore, it cools down the surrounding rocks. Rocks do not transmit heat very quickly by conduction. So you can cool it down. If you cool it down, you can actually use oil field equipment at 400 degrees Fahrenheit. 500 degrees Fahrenheit, and there's even a company out there trying to do it at 600 degrees Fahrenheit with nothing that isn't quote unquote off the shelf, although it's the high-end off the shelf stuff. And the thing which is exciting about this, if you can operate at higher temperatures, let's say we go from 150 degrees C to 300, so I'm not real good at that conversion, probably not many of you in your room use centigrade, but 200 degrees is about 200 degrees C is about 400 degrees F, 400 degrees C is about 750 degrees F. If you double the temperature, you don't just double the energy output, you get 4 or 5 times the energy output. So what Fervo's been doing is they've been going hotter, 375, 400, 425, the next set of wells be at 450, keep going up that ladder, and suddenly you're getting more and more production per well, which also sounds like the oil and gas story, right? Some of your companies are undoubtedly involved with unconventionals and trying to find ways to get more out of each well, and that's what we've been doing really well for a long period of time. So a lot of work going on this, super hot rocks. And closed loop. Closed loop is a really novel approach. It's designed to eliminate any chance of induced seismicity associated with water interacting with natural or man-made fractures. If you think about you're in an urban setting, you're in a big metropolitan area, let's say you're just outside of Tokyo, justifying hydraulic fracturing might be hard to do. So what companies are doing is they're trying to design wells where cold water goes down one well bore, they use well intersection technology to basically connect up 2 wells in the subsurface and then comes back up the other loop. So there's a company called Ever that's doing that. This other company is saying I'm going to drill a big well bore. Down the middle of that well bore, I'm going to pump down fluid and then bring it up out the annulus and let it heat up using some insulated piping to minimize heat loss. The challenge with all this is that no matter what approach you use, you need an enormous amount of surface area. The reason we don't just drill wells in the Permian Basin and not frack them is that the surface area needed for unconventionals, because of the low permeabilities, is millions of square feet per well. Well, you need the same thing in geothermal. So it's this conundrum of how do I deal with, I have to move fluid relatively quickly down the wellbore to get enough fluid going around to turn my turbine, but my heat doesn't come in very fast. So they're trying to use these techniques to somehow get more surface area contacted. Don't have time to dive too deep into it, but the really easy answer to this is if I'm operating at 400 degrees C instead of 200 degrees C, this becomes a lot more interesting. I can actually start generating enough electricity at a commercial rate to make it worth doing. So that is closed loop. Okay, the final, I got 2 more slides. The next one talks about what we have accomplished as an industry in America over the last 20 years. And what we have accomplished, I guess, is really what makes me excited about what could be accomplished in geothermal. So let me show you that one. The graph on the left, that's total US hydrocarbon production, oil and gas and BOEs. We were the world's largest producer of hydrocarbons all the way up through the early 70s, and then US production peaked. We had gone through all of the onshore conventional fields. We had gone into the shallow offshore, brought it out to the shelf edge, and we were starting to move into deep water. But production just couldn't keep up. Alaska was brought online in here, the deep water fields. We were going down, and that looked like that was going to continue, right? We were building LNG import terminals at the start of the century. So we were going to need to bring in gas. My company was looking at how do I take the gas in Prudhoe Bay and build a 4,000 or 5,000 kilometer long pipeline down into the US, which is going to cost tens and tens of billions of dollars. And then along came unconventionals. And look what happened to that curve. Nothing like that has ever happened before in our industry. I mean, that is what many of you in this room are involved with accomplishing. And today, we're a little north of 36 million barrels of oil equivalent, more than doubled the production in 15 years. Still going up, production per well still going up in the Marcellus and the Permian. Plateaued maybe a bit in the Eagle Ford, but lots of reasons to say America has a very vibrant industry. In fact, it's so vibrant, our main problem is we tend to grow production at too fast a rate and prices go down, and frankly right now is one of those moments when we're also starting to see that pressure, right? Saudi Arabia and other OPEC countries are trying to bring more oil back on the market, and we're still growing our production here in America, and there's just too much. But think about geothermal. I mean, this is like less than 2 gigawatts for the last third of a century. Now, if you apply this technology, what could happen? I mean, we're starting from a very low point, so growth is going to be significant no matter what. But could you create something like this where, suddenly 30 plus years out, a quarter of America's electricity is being generated by geothermal? I mean, I think that's possible. It would be really interesting, probably for almost everyone in this room or the companies you work for, because as I said, almost all the technologies being used are the technologies that come from the oil and gas industry. Almost anyone who works in oil and gas can learn to work in geothermal. There are some nuances to learn, and there's some really smart people in the geothermal industry, so I don't want to make it sound like there was a bunch of dummies and then we came along and saved them. That isn't what is happening. It's combining the knowledge in the geothermal world with the technologies and capabilities in oil and gas, which is changing things here. And just to give you some assurance or make you think, well, this is possible, this is a picture from the site out in Utah where Fervo is building their Cape project. This bill is directly adjacent to where the Forge wells were drilled. None of this was out there when your rig was there. This is going to be, this first phase here is 100 megawatts of electricity generation, and they're going to have 500 megawatts when they're done in 2028. When that comes online, that will increase the amount of electricity being generated by geothermal by 25%. So a huge increase. And there's a lot of places out west where this same approach could be laid down and developed relatively quickly. So that's all I've got. I'm going to leave this up here. There's a place you can pick up these slides, and Scott, you have a copy of them, so you're welcome to share them. But on my website, I have this slide deck plus a whole lot more. And in the back of the slide deck, there's a whole bunch of references if you want to pick up any of the kind of the details. Like I said, this is high level. If you want to dive deeper in any particular technologies like cementing or how to prevent scaling or how to drill better wells, glad to do that in the Q&A. So that's all I got.
I guess I'll ask the obvious first question,
yes.
if you don't mind. So looking at the map, our friendly hot rock is a long way from the light bulb. How is electricity transmission? Is that capacity growing? Is there structure there going in place?
Yeah. So two things. Scott's question is a good one, right? Because oil and gas are generally pretty fungible, and we have such a beautiful infrastructure in America as far as being able to move oil and gas around. Obviously, the electricity grid is not nearly as robust. There are places where is excess capacity. The particular valley that Fervo is working in actually has high voltage transmission running from there to California. They're selling most of their electricity into the California market. The hyperscalers are getting real interested in this because they look at it and go, well, I tell you what, I can put my data center right next to your geothermal field, and I can just use fiber optic cable to connect me to the world. And apparently transmitting data through a fiber optic cable is a whole lot easier than building out the electricity grid. So rather than bringing the electricity to the data center, you bring the data center to the electricity. So, I mean, there's some interesting innovations, but more needs to be done. America, if we're going to use more and more electricity, and it looks like we are, whether we electrify our vehicle fleet and or, all these AI opportunities, I mean, we need better transmission. So if you know of anyone in a position of power and influence, you might plant that bug in their ear. Aaron.
It is interesting. Everybody wants electricity, but nobody wants a power line.
They don't want power. Yeah, it's not in my backyard thing. It's kind of unfortunate. I mean, I've traveled the world a lot. I've spent lots of time in China. China is building loads of electricity transmission. They're using not just the approach we use here in America, which is kind of an AC transmission, which isn't that efficient, but they're using DC direct power transmission. I mean, we've done that in the past in America. We've taken the hydropower from Oregon and Washington, shipped it to California with DC lines. So building some big DC lines that are very efficient from the west to the east, I mean, could be a solution.
So I have a serious
Yeah.
question. So do these products have any degradation? Oil and gas, obviously they have depletion, the wells get lowered over time. Do these lose heat, or is there enough heat to keep sustaining the projects?
Yeah, so let me answer that first for EGS and then talk about the others. As I mentioned at the outset, the way EGS had been done, degradation was a huge problem. You were just, you were creating one fracture plane or a closely spaced group of fracture planes, pumping tens of thousands of barrels of water into it, and literally in months to a year or so, you were starting to get a lot of cold water at your producers. What you're doing here is creating, with the horizontal wells, a lot more surface area, but there are pitfalls, right? I don't know how many of you have ever worked on big water floods. I know Rick and I were talking about it, where you're pumping water into an oil field. You'd like the water to kind of sweep the oil in one nice, efficient front to the producer, and everything's great. But you get short-circuiting, right? You can get short-circuiting with these systems as well, particularly if you have pre-existing faults and fractures that are highly conductive. So one of the things we do in oil and gas, particularly in areas like the Eagle Ford and the Montney, which up in Canada, which has a lot of faulting and fracturing, is being very careful where we locate our wells relative to known faults and fractures. So you're gonna have to do some of that. Skipping stages if your well does encounter a problematic fault. And remediation, how to shut off problem zones. I mean, we do loads of that in water floods. So a lot of things there. In hydrothermal, you can have problems with that as well. You can imagine a natural system, if it doesn't have aquifer support, if it doesn't just keep feeding in more and more water, you're gonna have to start injecting water in to kind of provide artificial support. So you can have problems with cooling there. So you want a relatively long plateau. And this is more like an LNG project than like a unconventional well down in the Arkoma Basin. You want like a 10-year plateau so that you can monetize the cost of the plant you put at the surface. So yeah, a big area to look at. So thermal longevity, which is what you're asking about, Aaron. Water losses. So if you're moving millions of barrels of water around one of these systems, if you're losing 10% of the water you're circulating, the cost of the water makeup is very significant. And then induced seismicity, right? If you're losing a lot of water, you in Oklahoma, I don't need to tell you about what happens when you put tens of thousands of barrels of water away in the basement. you get induced seismicity, right? So you don't want to have water losses. So you want to design your well field to minimize water losses and maximize thermal longevity. So really, really important topic you brought up.
How long can you run these wells without cooling the surrounding rock? And then
Yeah. So it depends. I mean, right now, like in an EGS horizontal system, you know, the further you put the wells apart, the longer it'll take. I mean, you basically start cooling from the injector towards the producer, and you have a thermal front. So on day one, you know, all your fracture is hot, and you know, even on day 200, only a few feet away from your injector is actually cooled off. The rest of it is at reservoir temperature. So how far apart the wells are, if you drill a longer lateral and slow down the rate at which the water's moving through the fractures, that helps. So there's a lot of different engineering issues here. I've hit this at a really high, simple level, but there's tons of work here for reservoir engineers, completion engineers, you know, anyone who wants to think about, you know, essentially that topic, Scott. How do I maximize the time before that cold water shows up in my producer? Because these plants, you tune them for a particular operating condition. So like Fervo's saying, I'm going to be operating at 400 degrees Fahrenheit. The plant will generate the best electricity or convert heat to power in the best way at that temperature. If you start falling off in temperature, suddenly your efficiency starts going down and down and down. So yeah, you need to want to.
does Fervo think they can get 25 years out of a well?
I don't know about 25 years, but yeah, definitely, you know, decade type performance. They're trying to do things to achieve that and have a series of remediation tools available if a well encounters a problem. How do I shut off that short circuit that is getting the cold water there too fast? Yes, Matt.
So in states like ours where we may not have the best rock for geothermal,
Yep.
and one of the first things, you know, I was deep diving in this rabbit hole, but energy storage. So is that where we come into play? Like, hey, you know, we drill wells to go heat up water with intermittent, you know, power structures.
Wind and solar, sure.
Wind and solar.
Yep.
We utilize that. We, instead of putting that energy capacity into batteries above ground,
Yep.
we now heat up, you know, water down the wells.
Yeah. So there's a company called Sage Geosystems that is looking to do just that. They're going to be hydraulically fracturing horizontal wells, pumping water into it, and they're using a combined sort of geothermal pressure storage. Dilate the fractures with when you pump the water in, and it heats up while it's sitting in there, and then when you need it, it comes out, and you use both the pressure and the temperature to generate electricity. So you have those types of options. I wouldn't write off Oklahoma for, you know, some type of, you know, power generation, because the drilling technologies are advancing so quickly. I mean, you know, I saw a world in the unconventional space which evolved at a pace that no one could have imagined. We were looking at using multilaterals in some basins where we said, boy, we got to drill, you know, 12,000 feet before we kind of kick off. Let's put a bunch of multilateral hydraulically fractured well bores down there. But the drillers got so good at drilling to 12,000 feet that it didn't make any sense to go through all the challenge of building a multilateral well. So, you know, maybe you have to go deeper here, but it may be very competitive in the long term with energy. Yeah, well, or it may be better than wind with batteries, or even wind with.
Batteries are expensive and hard.
Yeah. So, I mean, there's a lot of stuff that's going to evolve over the next 25, 50 years. You know, I wish I was, you know, 20 years old again. I'm 66, and you know, I'm doing more of the, you know, helping other people think about this and driving it myself. But there's a lot that's going to be discovered, and I don't want to tell you that, you know, all the answers are out there, because most of them aren't. But I wouldn't write off Oklahoma. You've got tons of capability here, right? You know, this was the Saudi Arabia of the world in the 20s, right? The world's largest producing province was in Oklahoma. Probably not going to regain that status, but wouldn't totally write it off.
Maybe not by oil, but
Now, maybe something else.
sure do have a lot of well bores that are open up right now.
Yeah.
Is there any use for old depleted oil and gas wells in this aspect?
Yeah. Matt and I were talking about that at lunch. There are, I mean, one of the challenges with the old wells for the type of power generation I was talking about is the wellbore casing sizes are generally too small. I mean, if you want to be doing 25 to 50,000 barrels of fluid a day, you ain't going to do that with most of the wells we've put in the ground. But there are, some other uses. And I've been talking about power generation, but in large parts of the world, Europe and Asia, district heating is a widespread use of heat energy. This would be an area where instead of you having a heating system in your home, hot water's piped in, or in a city block, none of the buildings have their own heating system. So in the winter, as it starts getting cool, they simply open up some wells and hot water flows through a series of pipes and everyone gets their heating from district heating. And you don't need as big of a wellbore for that. Yeah?
Well, with the volumes of fluid you're moving, it would appear you need some pretty large casing size, but
Yeah.
what do you see in terms of corrosion?
Yep, so corrosion and scaling are two issues that you definitely want to think about in this space. Obviously with corrosion, I mean, it's just like oil and gas. We're going to have to understand the fluids, understand what they're interacting with in the rocks, and get the right chemical treatment. So chemical companies, there's a great future for you in geothermal. Scaling's really, I'd say, even bigger than corrosion. Because, when you have something at 400 degrees Fahrenheit, and then you're eventually at the surface going to cool it down, back down to almost ambient temperature, all kinds of stuff gets picked up and then it wants to drop out, and how do you manage that? You don't want to scale up your piping. You don't have to worry with these, they're called organic Rankine cycle power plants. You actually take the hot fluid through a heat exchanger, and the fluid turning your turbine is actually a hydrocarbon-based fluid. So the fluid from the subsurface never touches the turbine, but you can scale up your piping, or you could scale up those fractures, right? I mean, all of those are bad things. So, yep, chemicals are important. You had another question kind of in the back there that I didn't get to yet. Yeah.
Is the turbine generating power plant, is that installed near the well?
Yeah. Yes. Yeah, I mean, you don't actually want to transport the heat very far at the surface because you're subject to cooling, right? So one of the innovations Fervo Energy did is, by using directional wells, you can build just like a big pad. If you go out to the site, I mean, it looks exactly like something you'd see at one of our oil and gas sites in any of the unconventional basins. 15 or so wells on a pad, and then you build the power plant right next door. Now, if you were using all vertical wells, like the older fields, you put the vertical wells down all over the place and you have to pipe all of that fluid back to a plant. And so you have all kinds of surface piping, which isn't really efficient. But the new go-forward approach almost certainly will minimize that and plant wells co-located. The plants are going to get better. Right now, the efficiency of changing heat to power isn't that good. I mean, it's in the teens. So you can imagine there's a lot of companies, Baker Hughes, a company called Turboden, which is owned by Mitsubishi Heavy Industries, Ormat. They're all looking at how can I make my power plants better. And also there's a number of startups out there saying, can I modularize these things, come up with some innovative designs. So you'll see things there. So subsurface, huge amount of innovation, almost all driven by oil and gas. Converting heat to power, you've got a number of power plant companies working in that space. And as I mentioned, there's a lot going on the commercial side with companies trying to figure out ways to get the power to the end user or the end user to the power. Some really interesting commercial approaches being done with some of these hyperscalers to say, I'm going to take power from Utah, take it across the Nevada grid, bring it to California and use it there. That type of thing in America doesn't happen very easily. I come from a state which we basically have a wall built around our entire electricity grid. It's, we got ERCOT and no one else can come in or out of it. Down the road, it'd be nice if we could generate and transmit electricity more easily across the United States, but there's tens and tens of, little utility or big utilities, all of which have their own little domain, and they're not real happy about playing with each other, it seems. So I don't know. There's a lot of things to work on, whether you're a commercial person, an engineer, or anything else, geoscientist.
Any more questions? Matt, would you tell the group how they can get to these?
We do have a YouTube channel, and we'll put this video up. I'll add the slide deck to the back of the YouTube video, and that way everybody can access that. Just so we have API OKC on YouTube.
Good.
Thank you.
Thank you for your time, and appreciate it. Thanks.